on that because we had some discussions on your working out, etc. in the previous session. So in the meanwhile, I'll run this. But in case any one of you has any kind of queries to be addressed, etc., please post them. I'll spend some time trying to address the query. So by the time this program also will run, and we'll be able to discuss some of the aspects. Okay, now I hope my screen is visible, Dev. Sure. So possibly you can have your questions, then let it run, and then we will discuss. Otherwise, if you don't have questions, then I thought I'll go ahead with the conceptual part of the support vector machine. This is a slightly more complex aspect, but yeah, we are going to deal with some of the only essential elements of the support vector machine. Because again, we will get into the implementation parts, etc., where the mechanism is more or less similar. So, does anyone have any queries on any of our topics till now? So, essentially, in machine learning, as I have been telling you, it's a way where we are trying to link the target variable with one or more feature variables. Now, what is the way the linkage is built? That is where the various algorithms are coming in. Perceptron is a very basic algorithm. Then we looked at logistic regression, which actually is a slightly sophisticated algorithm over the top of the perceptron, because there is a probability that is typically being predicted, not just a 1 or a 0 kind of a thing. Then we moved on to a KNN classification algorithm, which was more of distance-based learning kind of an algorithm. Right? So these are different kinds of algorithms. So today, in fact, I wanted to cover two, but somewhere I don't think time will permit. So today I will talk about only support vector machines. But in the meanwhile, if someone has any queries from the previous session on some, because last time Dev has actually mentioned that something is going out of overbound or something like that. So that's where I want things to be again back on track. If I need to spend a few minutes to bring those things or to connect something, I don't mind doing that before we move on to the next algorithm. But if you don't have any questions, then probably I'll move on. Okay, then, okay. If anything, showing error again and again. So what does that mean? Can you give an example there? How do we get to know what is error in the code? See, many a times, if you are running line by line, right? Sometimes I am running, so this is again an interpreter-based code here. So many a times what can happen, you can run just one line, you can print just run one line. So sometimes I may be integrating 4 or 5 lines and I'm making it as a block. But if you are not that clear, then better run only one line per block and immediately try to print it. So that is what can give you. There are some other debugging mechanism, right? But most of the time, this would be more easier. And especially if you are going into a loop kind of a thing, a for loop or something, better take only one instance of that loop and then try to test it end to end. So many a times in case you are getting stuck at a particular code, and especially that problem will come when you are running a 4 or 5 lines in one single block. You don't know where you have got stuck, but at least here you will get a very clear-cut error message also. So based on that error message, you may have to dig again back and then look at probably running only one line in that. So only based on the examples we can respond on those things. Most of the time, the error message that is displayed is more meaningful also. So probably the best thing is Google out on your error messages. To a large extent, you will find the solutions for the same. Right? Those things will come with more and more of a practice itself. Most of the time, Googling out on your correct error message will give you the proper solution as such. Because there are lots and lots of help that are typically available. At least Python has matured a lot. You can easily find help on most of the typical problems that you are working with. Okay. Okay, then let me try out with this support vector machine. Logically, we see that this is a very, very complex algorithm. Though it appears very much simpler, but probably out of the various machine learning algorithms, we see that these are some of the very complex algorithms. So the major thing is, it is actually built on some premise. The premise on which this algorithm is built is a concept called hyperplane. So the concept that it says is there is something called a hyperplane which can separate the classes, can separate the defaulters from the non-defaulters, the yes group from the no group, the zero group from the one group. So the basic premise on this entire model is it assumes that there is a hyperplane, there exists a hyperplane that can very well separate. So basically, if I'm talking about a one-dimensional data, let's say I have some zeros and some ones, right? Only one-dimensional data. There exists a kind of a hyperplane. Or let's say, so here the hyperplane is just a point. Or if I'm talking about a two-dimensional data, where some zeros are there, some ones are there, there exists a hyperplane. Here the hyperplane is a line. There exists a hyperplane that can segregate zeros and ones. Right? So what we are saying here is this, if it is a two-dimensional data space, so which means if there are only two variables, if I'm talking about a two-dimensional data space, it means I'm referring to two variables. Probably x1 is there here, x2 is there here. So if I have two variables, the hyperplane is a one-dimensional figure. one-dimensional flat figure. So which means it's a line. One-dimensional figure is typically a line. And similarly, if my data is just a one-dimensional data, which is like only x1 is there, then my hyperplane is a zero-dimensional object, which means it's just a point. And similarly, if my data is a three-dimensional data, which means there are three variables, x1, x2, x3, which are plotted in 3 dimensions, then my hyperplane is like a rectangle, two-dimensional flat figure. So my hyperplane is a rectangle which can segregate zeros and ones. So that is the typical premise behind the concept of support vector machine. So we are dividing the data. The basic thing that we are saying in support vector machines is we are dividing the data based on one n-1 dimensional hyperplane that is segregating the zeros from the ones. So that is what is the basic premise based on the development, so based on which the support vector machines have typically emerged. Now this support vector machines, they started, so basically we will talk about the maximum margin classifier. The first one, this is the one that I'm right now, the two figures that I have shown, they refer to the maximum margin classifier. From there, the evolution has gone towards what is called as a support vector classifier. And from there, what is typically called as the support vector machine. So there are 3 stages out here. So we'll look at all the 3 stages. Okay. So probably in many cases, this example that I considered, the two-dimensional example, right? Let's say I have all the zeros like this and all the ones are like this, right? I want to segregate the zeros with the ones. So obviously I will draw some line like this. So because this is a two-dimensional data, the segregator is a one-dimensional hyperplane, which is what is a line. Line is segregating the zeros and the ones, right? So we are this is called as, this line is called as a hyperplane. So this hyperplane is separating the classes, 0 class from the 1 class. So the points that are on one side of the plane, hyperplane, they would be categorized as 0, and the points that are lying on the other side of the hyperplane, they would be classified as 1. Right? And in this case, it is very clear that the separation between zeros and ones is very, very perfect. Right? So now here, can I take this line or should I take this line? So they are all separating, right? This line or even this line or even this line. They are all separating the zeros from the one. Now, which one do we talk about? Now, this is where the first concept comes in. You look at the maximum margin. You look at the maximum margin classifier. So whichever is the way you draw, right, probably right, if I draw something like this, you see here, from here, look at the margin on either side. So basically I can go from here up to here only. Whereas from here, I can go up to here. So basically the margin is this much, right? So somewhere in the middle, I draw another line. So this line will create the maximum possible margin to both the sides. So look at in such a way that the margin to both the sides is maximized. Why the word machine is not that it should be support vector classifier. I'll come to that, why it is called as a machine. As I told you, there are 3 stages for the same. So right now I am in the maximum margin classifier, right? So this is the maximum margin classifier. For the machine, just wait for a couple of minutes. Okay, so I'll take you through all the 3 stages. Right. So the second stage is the support vector classifier, and the third stage we are ending up into the support vector machine. Okay, so this is the maximum margin classifier. So we are classifying in such a way that the margin is maximized. Especially this mechanism comes into picture. Especially this mechanism comes into picture when they are perfectly separable. When there could be some kind of line that could be drawn, line for a 2-dimensional, it is like a line. For a n-dimensional, so if I have n variables, we are visualizing about a n-1 dimensional plane. So it is very hard to visualize the n-1 dimensional plane. So that's the reason most of the times we talk about the examples with respect to a 2-dimensional plane, 2-dimensional data, and a 1-dimensional hyperplane, which is like a line being drawn to separate. So this is the first stage in a support vector machine, where we are typically talking about perfectly separable kind of observations, and we are able to draw a kind of a hyperplane, which is like a line, which would maximize the margins between the 2 classes. So I would look out for the 2 classes borders, and I would see whichever is the one that is maximizing the margin. So that is where it's called as maximal margin classifier. Okay. So it could be drawn for an n-dimensional data maximum. So if the data is non-linear in nature, so just wait, please. Okay. So I think we are going step by step. So in case there is such a kind of, in case there is a possibility of such a kind of a separator, I'm only talking right now. I'm talking about the instance where there is a proper separator that is there between the classes, right? Now, the second instance that I am talking about is, what if they are not perfectly separable, which is the most common problem. What if they are not perfectly separable? So probably if I'm talking about unidimensional data, let's say I have zeros, right? Probably I have some kind of zeros, I have a 1, then I have a 0, then again I have some kind of 1. So let's say I have some such kind of a data. Then what if they are not? So here, it all depends. Now, if I put a point here, a separator here, then it looks like there is a 1 that is, so if I say before this, they are all zeros, and above this point, they are all 1, then this is a kind of a misclassifier, right? Or probably if I put a dot here, Rather than putting a separator here, let's say I put a separator here. Then, or probably I put a separator here. I put a separator here saying below this they are all zeros and above this they are all ones, then this one will become a misclassifier. So obviously I cannot do a complete classification, perfect classification in this kind. Similarly, if I'm talking about a two-dimensional data also, let's say x1 and x2 are plotted like this. Two variables I have plotted like this. So we have probably something like this, right? So just by using a line, I really don't think I can very well segregate the data unless I think of something like this. So in that case, I'll put a 1 here as well. So in this case, whatever I do, I may not be able to perfectly segregate the data, right? So without misclassification, though the data is a two-dimensional data, and I will have to use a one-dimensional hyperplane, which is a line, I will not be able to segregate the data perfectly. I'll not be able to segregate the zeros and ones perfectly. So this means there is a possibility of a bias variance trade-off that can come here. Right? Bias variance trade-off that can come here. Probably in this example, we can see that example also you see here. Probably if I'm having all my zeros somewhere here, right? One is here and all ones are here, right? So where we put our separation, let's say I put my separation here. Think of it. I put a separator here. Only one is misclassified. Below this, they are all zeros. Above this, they are all ones. Right? Only one value is misclassified in this case. But think of a scenario. Right? Think of a scenario probably coming somewhere here. A new point coming somewhere here. Automatically, this would be classified as a 1. Because this is where we have put up our cutoff. So if a point is here or here, it would be classified as 1. It would not be classified as 0. So which means in this case, the variance is getting increased. Right? Whatever we are predicting on our test data, that is actually a kind of a mistake. Right? Because we have put our classifier here. But on the other side, you think of it, if you have put your classifier here, if you have put your separator here, right? If you have put your separator here, you can very well see here that anywhere here, if there is an observation, right? If there is an observation here, this would be very much classified as a 0. So here what happens, your bias is higher, but your variance is going lower because to a large extent, this group is containing all the zeros only, and you are able to classify all of them to be 0 itself. So it depends on how you are treating that particular class separator. So if you are determining your separator somewhere here to just avoid this particular one, you might be getting a lower bias, but you might end up with a higher variance. Whereas on the other side, if you are putting here, you might end up with a higher bias, but a lower variance. So a simplistic model, which might result in a higher bias, but a lower variance, or depending on the other side, it might go for a lower bias with a higher. But keeping all those things aside, now what we are simply saying is we will be introducing something called soft margin. right? We'll be introducing something called a soft margin. So what we say is, so you put some kind of a margin called epsilon. You put something called a margin called epsilon, which we are calling as the kind of distance between the threshold and the observation. So you are putting some kind of a margin. So what is that we are saying again if I refer to the same data? So I will say, I'll put, let's say, this as my one margin, and I'll put this as my second margin for zeros. So this is the margin for zeros, this is the margin for one. And which means, so here, if I said that this is the distance between the threshold and the observation, which means in this area, the misclassifications are allowed. So as long as, now you see the difference. So I am not bothered about some small misclassification, right? As long as the error is within this epsilon limit. So the misclassification is fine for me. So we are bringing in some kind of a soft margin, saying I want to maximize this margin, no doubt. And within this, if there are misclassifications, that is pretty much fine, right? So inside the margin, I am very much fine with the misclassification. So rather than saying every time there will be a perfect segregation, so basically in the two-dimensional also, what is going to happen? If my zeros are here, and if my ones are like this, and let's say there is a one like this, okay, so then I might very well define, okay, this is my one, this is the margin for ones, right? This is the margin for zeros. And within this margin, the misclassifications are very much possible. Within this margin, so basically here in the middle, if I put, so within this margin, the misclassifications are very much possible. Now on the either side, these values which are actually going on the border, they are typically called as your support vectors. So this is this one is a support vector, and probably this zero is a support vector. So these are typically called as your support vectors. Now these support vectors, so they are creating a kind of a margin, right? And based on that margin, we are more and more interested in allowing for misclassification within the margin. So the data points are typically called as your support vectors, right? So basically the one which is this is a data point, x1 and x2 combination. So the data point is typically called as your support vector. You are right. Okay. So these support vectors, between the two support vectors, you have a margin, and that margin is a soft margin because we know that there are some kind, so it's like a maximum margin that you can allow, and at the same time there could be misclassifiers also that are possible within the margin. So distance between the threshold and the observation. So we are actually putting some kind of a threshold, and the observations on either side are your support vectors. So up to the support vectors, whatever is the distance, that distance is what we are calling as our soft margin epsilon. So this model support, so with sometimes what could happen, both scenarios are possible. Sometimes you may have a line that you can draw, right? I'll tell you something else. Right? Let's say something like this is there. So you may say, I will draw a maximum classifier, maximum margin classifier, the first mechanism, where there is a perfect separability. So this is one solution that you may say. Now, second solution, you may say, no, I will not go with that option. I'll draw one support vector like this, and I'll also draw another support vector here. Right here, there are two support vectors for that matter. Here there is one, but doesn't matter. Now this is creating a very big margin, right? And within this margin, I'm allowing the misclassifier. So there are two solutions. One is a maximum margin classifier solution, which is very much possible, but that solution is not maximizing the margin much. It's a very, very minute margin. So there might be a possibility of a new value. It might come a little bit misclassified as well, because sometimes I may have values coming out here. It might very well fall into 1, or it might very well fall into 0. So unless the gap is maximized, we cannot do a proper prediction on the testing data. It might work well on the training data, but it might not work well on the testing data. Again, giving you a scope for higher variance. Whereas if I am giving such a kind of a big gap, probably my bias could be much higher. I'm clearly segregating the 0 and 1. Somewhere in between, we are allowing for the kind of an error. So it might very well be possible that the ones which are in the very extremes, they might get very well properly classified with a very limited variance there. So now, if I am allowing for such a kind of soft margins, there could be many possible threshold splits. Now I can split it here, I can split in a angular fashion. Probably I can very well think of some such kind of a split. So I can think of various such a kind of threshold splits. Now, because we are allowing for some, so we have to define what is our soft margin epsilon. So that much is the kind of a gap that I can very well allow between the two support vectors. That's the maximum gap that I can allow between two support vectors. So, which means there could be multiple such a kind of lines or such a kind of hyperplanes can very well be drawn, because the threshold split can very well be multiple in number. Now, this is where what can happen is the working with the training data and the testing data, the cross validation. You will create your training data and the testing data. So you can very well work out with the cross validation. So this cross validation, 5-fold, 10-fold cross validation can very well determine what is the optimal size of the margin. So you can very well set your margins, various margins, and based on those margins, you can very well determine what would be the optimal size of the margin. So you will rely on the cross validation, hyperparameter tuning, and the cross validation to determine what should be the optimal size of the alpha, right? So which means here, in this example, I am able to show you a maximum margin classifier as well as a support vector classifier. Support vectors are on both the sides of the threshold in a margin, in an interval of a margin. So those support vectors on either side of the threshold, which are within which there could be there could be misclassifications that are possible, right? So this is the second problem. So we have moved from maximum margin classifier to a support vector classifier. So these are the two different instances. Of course, when you are doing it in a practitioner's perspective, everything will be with one single piece of code itself. But just that I wanted to explain some basic concepts, right? And so that it can help you in doing any kind of explanations anywhere. So that's where I'm trying to share some of the basic. I mean, I may not get into the high-end mathematical calculations associated with this, because to a large extent, my target audience also are functional people who want to get into the data science and all this. So from a functionality perspective, typically I explain all these concepts, but typically getting into the mathematical equations and all, probably I suggest that you can refer to them in some of the textbooks. I mean, to whatever extent the basics are required, I can typically explain it here. Okay. Then, so here in these two scenarios, what are we saying? First scenario is the perfect separation, which is in that case, we are talking of maximum margin based classification. In the second case, not perfectly separated, but with some epsilon, I am able to create a separation. So some misclassification, right? So the first example is of maximum margin classifier, whereas this one is an example of support vector classifier. Now, there could be some kind of problem. The third, I'm going to talk about support vector machine. So what is happening in support vector machine is, even after, so let's talk about some, again, a data set. These are something that classic examples that people give. Let's say I have a data more like this. My zeros and ones are more like this. So you do any kind of a maximum classifier, maximum margin classifier does not work at all. You put your separation here, then these are all misclassified. You put your separation here, then these are all misclassified, right? So you put your separation here, then some of these are misclassified this side, some are misclassified this side. So you do whatever. And you put any kind of a maximum margin, so you put a kind of threshold, you put a kind of a soft margin. It is very, very difficult to segregate by even after putting some kind of a soft margin here, right? So even if I am allowing for soft margin is nothing but that particular margin in which some misclassifications are very much possible. Now, I don't see any such kind of classification here, right, for this kind of a problem. Or probably in a two-dimensional space, look at it like this, a very classic example that we generally say. Let's say you have data like this. You give me a line which can take some kind of threshold or some kind of soft margin, but within that soft margin, it can very well segregate. So it is not possible in these examples, right? Now, that is what I think our friend Paras was referring to. What if they are non-linearly available? Now, this, so it's a very simple example. I'm not able to segregate them, right? Now, this is where we bring in some concept of kernel trick or kernels. We bring in some simple concept of kernel. So these kernels, they actually help us to project the data. This is a very, very classic concept. The kernels will help us to project the data into higher dimension. Now, what is happening? I'll give you a very simple example. Now, in this case, let me do some kind of transformation. In this case, I'll do some kind of a transformation such that this value will be around 0. This value will be set to 0. Right? And probably these are the negative values. These are the positive values. Okay? Then what I'll simply say is, for all x, I'll create one more dimension called x squared. So instead of one-dimensional data, now I will make it a two-dimensional data by just doing one kind of a squaring. By doing a simple squaring. So which is nothing but, so if I am taking one x as a vector here, I take a kind of a transpose of this vector, right? So I take a transpose of this vector or something. So, or I do a kind of a dot product of this vector. So it's a simple squaring, right? So what will happen now? I will have my two dimensionals now. Now I'll have my x here, I'll have my x squared here. Now you look up this scenario, wherever there are ones, now this is a 0. So this point will correspond to 0, 0. This 0, 0 is at here. Then let's say this point is at 1. So 1 and 1 squared. So this is where I have a 1. Then this is minus 1. So probably minus 1 and 1, I have a 1 here. Then this becomes 2, 4. So I have a 0 here. 3, 9. I have a 0 here. 4, 16. I have a 0 here. Minus 2, 4. I have a 0 here. Minus 3, 9. I have a 0 here. Minus 4, 16. I have a 0 here. So I made this one-dimensional data into a two-dimensional data. So I'm getting a kind of a parabola. Now, because it's a two-dimensional data, my hyperplane would be a line. I'm able to segregate. I'm drawing a line like this, and I'm able to segregate all my ones with the 0. Even in this example, even without any kind of soft margin, even without any kind of a soft margin, I am able to segregate out here. Similarly, in this kind of a problem, I will project all these. This is a two-dimensional data. I will project them into the third dimension. Right? When I project them into the third dimension, the ones in the middle, you see the ones that are surrounding it, they become a kind of, they become so if I'm dragging it in the form of a cone, the ones will come to the top of the cone and all the zeros will become the bottom of the cone. Right? Just I'm pulling out the center. Just imagine like this, right? I'm converting this into a three-dimensional object, the two-dimensional data, where the ones that are there in the middle, I'm pulling them out. So let's say it becomes a kind of a cone or a kind of a cylinder. No, it's a cone. So the ones in the middle, they are dragged towards, which means they are becoming the tip of the cone, the top portion of the cone, whereas the zeros are typically lying at the bottom portion of the cone. Now I will cut the cone in the middle through my two-dimensional hyperplane. So rectangle is my two-dimensional hyperplane. I will cut it in the middle. So which means it would still be in a position to be segregated. Now this is what is typically called as kernel function. So these are called kernel functions. Right? You actually, so basically what we have done in this case is what is called as a polynomial kernel. Right? I have typically created one additional variable. I have created one additional variable and one additional dimension, right? By doing a squaring of the current variable. Or I can do a cubing of the variable. I can do some such kind of activities. And based on that, I can very well segregate the zeros from the ones. So this mechanism of using the kernels and based on, so which means there is some, that is the reason they are called as machines here. So there is some extra tricks that are performed on the data in a mechanized manner, right? There are some extra tricks that are performed on the data in a mechanized manner where various combinations are being tried out. So different polynomial. So we have different such kind of kernels that are available. One is a simple linear kernel, or there could be a polynomial kernel. So there are some radial basis kernels, which is what you can very well think of in this kind of an exercise, right? So there could be a radial basis kernel, there could be a sigmoid kind of a kernel. So there could be different kernel tricks that are applied. So because there are various kernel tricks that are getting applied, so but the kernel is nothing but it is some function where data is projected into the higher dimension, and I don't know how many dimensions higher have to come. Sometimes after I project to the second dimension also, I may not get a proper separation. Then I may have to go for a third dimension, fourth dimension also. So until I get a proper separation between the, and I mean, to a large extent, get a kind of a proper separation between the different classes, right? So we can very well think about a polynomial kernel, which is like a takes a square dimension. So generally, what happens is, right? It's as good as saying, let's say I'm talking about 3 points as a part of X and my Y also containing 3 points, right? My XY plane. Now it can very well be possible that these two can be mapped into a next dimension also, right? Probably I can think of so there are 3 points here, there are 3 points here. I can, if I want to go for a squared dimension, right, polynomial, probably I can very well think of XY plane altogether, and I can take the square of it. So as a dot product, it can become 1 into 4 plus 2 into 5 plus 3 into 6. Right? So basically, I can very well think about a squaring of this. So I mean, or I can take 1 into 5. This entire thing I can take it as a square. So possibly it can become 4 plus 10 plus 18 squared, which could be 32 squared or 1024. So this is what is happening here is if I want to take it into a squared dimension. So basically all I am taking up here is if there are multiple variables to be considered, right? In this example, I have taken only one variable x as an x squared. Now here if I am having x1, x2, x3 as three, right? If I'm having x1, x2, x3, y1, y2, y3 kind of variables, then probably if I have to take a kind of a square of them, or if I want to take a polynomial kernel, then probably this kind of, I mean, there is a kind of a computation. This can happen in this way to map it to the next higher dimension. So what we are simply looking at in all these exercises is probably the system can do the remaining calculation. Your observations. So if it is a three-dimensional data, I can very well take it to the fourth dimension, fifth dimension by adding one more computation like this. So along with these three, the fourth computation will come, which is something like this. Now, once I get into the fourth dimension, then obviously I should be able to segregate the data based on this, based on a three-dimensional segregator. So this is where we are bringing in what is called as this kernel trick. So it is actually avoiding kind of recomputation of the points in the higher dimensional space because it uses the simple dot product of the various vectors, and based on that it does the transposition. So basically the calculation is primarily simplified for us. So we can very well specify what kind of kernel we would like to propose. So this kernel is also becoming what is called as a hyperparameter. What kind of kernel you are planning to go with. So the kernel also becomes one kind of a hyperparameter. It's as good as, if I have to talk about in a very layman term, if I am talking about a two-dimensional data, let's say I have only two variables x1 and x2, then I can think of a simple equation like P0 plus P1x1 plus P2x2 equal to 0. So that's the equation of a two-dimensional kind of a data, right? But if I am talking about a p-dimensional data, then I would have simply called b1x1 plus b2x2 plus and so on bpxp is equal to 0. Now, if this entire value, if it is coming out to be greater than 0, I will put it into one group. And if this value is less than 0, so that is what is the kind of a separation that is coming up. I will put it into the another group. So basically, if I want to talk about the mathematical thing here, so I want to still maximize the margin, right? If I'm talking about this, I will maximize the margin between the two support vectors, where I want to really look at the overall weightage of all my coefficients are this beta naught, beta 1. So these are all my coefficients. The overall weightage of all of them should be summing up to 1, right? And so basically I can think of, so I mean, my yi time, okay, let's not get into the mathematics of this. So basically, what I'm trying to say here, right, I don't want to get into, so the different kernel functions that are being used here, they do the transformation of the data, right? They do the transformation of the data into higher dimension. They do the transformation of the data into higher dimension. And one, so which means that two-dimensional, two variables will become 3, 4, 5 variables with the different computations that can come, because it will become two-dimensional can become 3, and now I have so now I have a 3-dimensional, then I can take it to a 4-dimensional kind of a data. So I am projecting the data into the higher dimension, and after that trying to see if there is any kind of a hyperplane that is going to segregate the data. So like that, there are different ways of projecting into the higher dimension. Different kinds of functions are applied to project the data into higher dimension. So I can use a simple linear, or I can use a polynomial or radial basis or sigmoid. Right now, these are the most popular kind of kernel function. And because there is the usage of a kernel function, which actually projects the data into a higher dimension before computing the hyperplane, that activity is typically getting translated. So it's not doing the classification directly. It is doing some kind of a trick to internally change the data, or not change, actually project that data into a higher dimension, and after that the hyperplane is typically. So the hyperplane is still a classification aspect, but projecting the data to the higher dimensions using the kernel functions, etc., is what is the associated with that support vector machine as an aspect. So that is how these are the 3 stages that are typically being called. It's a machine because it is trying to automate. It is trying to automate the various such kind of kernel functions, and then see which one. So, or if you are applying a particular kernel function, there is a kind of an automation step, because there is a black box that is coming in. So it's an automation step that is coming in an iterative fashion. That's the reason possibly it should have been called as a support vector machine. Right? Mathematics wise, even I did not get the preparation part of it as well, and it would go well about. So if someone is interested in the mathematics of it, possibly I'll share you some link for the same, because in a practitioner's perspective, we don't get too much into the mathematics unless we as long as we understand the overall flow of what is happening and what are the various dimensions that are coming into the process. So basically here, I want to maximize the margin, right? So one step is I want to maximize the margin, and along with that, I am fine with an error, which is like a soft margin. So I am fine with an error of some epsilon, right? Some misclassification is still fine with me. So after considering the misclassification into consideration, that epsilon, I want to maximize my margin, and so there could be some kind of a penalization of the parameters also that can happen. So this is where I want to restrict my overall. I'm putting a kind of a constraint that my overall weight should be sum of squares of the coefficient should be 1. So I'm putting a kind of a constraint. So this constraint is what is the regularization parameter, because I don't want the model to go as much. So basically, if something is solved with a 2-dimensional, I don't want to go into 3, 4, 5 dimensions. Now that is what we are putting a kind of a regularization parameter also on the top of it. So that is where the different solutions are typically going to crop up by using your support vector machine. Is that clear, at least to some extent? So possibly you can do some kind of a reading on the same, right? But when we go into our scikit-learn, more or less it looks the same. Whatever we have done for KN, the same process you will do for support vector machines also. So there is not much of a difference from that perspective, right? Probably if we see the approach that we have followed, right? We are initially importing the support vector classifier. Support vector machine can very well be used for solving regression problems also. along with the classification problem. Again, just like the way, if you remember, I think for the last 2-3 problems also for us, we are talking about these as hyperparameters, right? Now, for which kind of a problem, which kernel function is suitable, it's very difficult to make out, except for now if you have plotted only two, if you are having only a two-dimensional problem or a one-dimensional kind of a problem, while it might be very easy to make out, but if you are working in a multi-dimensional problem, right, with 10 variables or 15 variables, because you can't do any kind of a variable, it would be very difficult for you to decide which kernel function will work, right? So you know, in the machine learning, at least as far as I am concerned, or as far as my knowledge goes, people will always experiment with more and more combination. And whichever combination comes the best for their data, probably for some period they will continue that combination, right? Every time they will not run all the combination, but when a model is being run in the backend for the first time, all combinations are typically run and the best possible model is shortlisted. But after that, that model is continued for some time. So that is the typical process that is followed, because it's not easy to make out, right? It's not easy to make out, especially if the data is so in a larger dimension. For explanation, probably one-dimensional, two-dimensional, as you have seen earlier, when all my ones are somewhere close by, right? Then possibly it looks like I can do a kind of a polynomial transform or something like that. But when I go into a very high dimensional kind of a data with so many variables, etc., that makeout will become very difficult. So that's the reason we always say in most of the machine learning problem, the hyperparameter tuning will become a very important exercise altogether. So again, I'm going with the support vector classifier on the training data. Look out for the accuracy on the training data. So if it is higher than the null accuracy, then probably there is no underfitting of data. Then you test it on the testing data. You look out for a series of metrics. Probably you could see that these are the various various metrics that have come out. So probably some of them are interesting, some of them are looking pretty pathetic. So you could clearly see that this is the classification. Then you can also do the kind of a hyperparameter tuning. So now you could see here, there are three major kind of, so probably let's go for SVC. So you see here, so here if you are looking at, so this is a support vectors classification that you are saying. So we are talking about, so basically if I look at the equation, if I have to show you the mathematical equation. So you see here, there is a, so you see it's a versatility that is coming in, because you can specify different kernel functions, right? So sometimes you can create your own kernels. Probably I have not got to that stage, right? I would always try to work out with the existing kernels itself. I don't think I have that a kind of a knowledge space where I can create my own kernel functions and I work. But at some point, I was thinking of using some kind of a rectified linear unit kind of a kernel function. But again, I didn't know how to implement that as well. But typically, it offers you where you can create your own kernels also. But most of the time, I use the existing kernel functions and I run it in a kind of a loop to identify which problem can be solved to what extent, right? And the disadvantages are if the number of features is much greater than the number of samples, your columns are much higher than the rows, especially in a image classification kind of problems, etc. You will come across this kind of a scenario because every pixel will be treated as a different feature or a different column in a typical image classification problem. So you will find there the number of features is much greater than the number of samples. So basically in that case, the overfitting will become a much bigger problem. So you have to be very clear about the choice of the kernel function and the regularization function because so I wanted to show you the equation. I'm just looking for that. The function would typically maximized or minimized. Right. So possibly you should read through these notes, right? In case you are more and more interested towards the mathematics side of it, right? But I mean, I don't go one side. It gives me a kind of a solution to a problem. I don't. I'm not much bothered regarding the mathematics. I mean, I'm more of a solution oriented guy, but I typically see that there is some function that they specify somewhere here. The one that would be minimized or mathematical formulation. Yeah, this is the one. So here we are talking about whatever are the coefficients that beta naught, beta 1, beta 2 that I was talking about are b naught, b1, b2. So I want to maximize that b1 squared. So I want to minimize that b1 squared, b2 squared, that summation, because that is where I'm talking about weight transpose weight. And along with that, I'm bringing in a kind of a regularization parameter also. So where it is talking about the summation of the coefficient. So the more I am putting a regularization parameter, then the strength of the regularization is actually coming down and vice versa. And we are talking about this particular, so we are giving a kind of a error margin here. So this is the kind of a error margin, that epsilon that we were talking about. So I want my value, as long as this value is greater than or equal to 1 minus this epsilon, so I'm pretty much fine. So this is the kind of equation or a function that could be optimized when we are doing this support vector classification kind of a problem, right? By using the vector. And they do not provide probability estimates. These are so normally they don't directly calculate the probability. We use the five-fold cross validation, etc. And based on the number of correct classifiers versus wrong classifiers, the probability of misclassification is typically computed. Whereas in the logistic regression and all, the probability is directly computed as such. So here we are seeing one hyperparameter is my C. C is nothing but the regularization parameter. So regularization parameter, we are talking about higher the value of the C, the lower is regularization strength and vice versa. So what is that we are saying? I will give these are the right. The default value is 1. So I'll take a few values below it and a few values above it. Then the kernels, linear kernel, polynomial kernel, radial basis function kernel, or a sigmoid kernel. So these are the 4 different kind. Now in the polynomial, it can go with a square, cube kind of kernels as well. The second dimension, the third dimension, etc. Then sorry, degree, square, cube kind of thing. Or we can have a radial basis kernel, which is more like e to the power of there is so it looks more like a the normal distribution kind of animation function. Then we talk about a sigmoid kernel. The sigmoid kernel is 1 by 1 plus e to the power of minus x. So that kind of a kernel is typically applied. So like that, you could see that different kinds of kernels. Now, I don't want to solve any problem just like that. So I'll give all 4 combinations. Let the system decide. Then what should be the gamma value in some kernel function? So basically, gamma is one kind of a variable. Okay, let me just now kernel functions. So especially in radial basis kernel, as well as in the sigmoid, there is a parameter called gamma. You see here. So this is a Gaussian kernel, which is the radial basis function kernel. So e to the power of minus x minus y whole squared by 2 sigma squared. So you will find out the difference between the 2 vectors x and y. Find the difference between the 2 vectors. Take the dot product of that vector into vector, square it, and divide by 2 sigma squared. So this is what is a kind of a transformation. So you will take the difference between the 2 observations x and y, and you would take the difference, take the dot product, square the dot product, and then you divide by. So that is what will typically give you. So what should be that gamma? Because there is a gamma, which is again another parameter that is coming in. So the default gamma that is typically taken is it uses 1 by n. That is the default value. So if I have 10 variables, then gamma is automatically set to 0.1. But otherwise, you can also give, so you can, otherwise it will take 1 by number of features times variance of x. So whatever is the variance of x, that is what it would typically take. So there are a couple of, generally we do a scaling. So because when we do a scaling, you will always get each variable to be 1 only. Variance of each of the variables to be 1. Because we have done a standard scaling of the data already before doing this exercise as a data pre-processing. So the general thing is x dot variance would always be 1. Number of features times the x dot variance would typically be coming out to be the same as auto, especially if you have done the standard scaling of the data. So you can give your own specified values for gamma. You can give your own specified values for gamma. So these are the 3 major hyperparameters that come into picture, right? And in case you are going for a polynomial, then probably you can very well plan out with your degrees also separately. So there could be another hyperparameter for your as well. But otherwise, these are the 3 major hyperparameters, right? So, and then you can very well specify your gamma values. So the auto will always consider 1 by the number of columns that are there in your data, right? And probably you can very well specify your values of gamma. So right now it looks like 1, 2, 3, 4, 5 times 3 times 4. So 15 fours are 60. So 60 different combinations have come. So here I have anyhow commented it out. But generally what you may want to go with all 60, then you will have to go with a grid search. Or if you want to randomly take some number of observations and simply continue, then you can go with a randomized search. But generally these kind of problems, they will take quite a good amount of time. And because we didn't have much time today for the class, because I started off late, so I just commented these lines out. But in case you want, you can uncomment them and you can run this. So it's the same thing. So once you run your randomized search, so here randomized search, what it will do is it will not take all 60 possibilities, right? Probably, I don't think we should run it now. But the randomized search will take all only a subset. Generally, the base default is 10. So randomized search will simply take 10 different subsets of these combinations. And out of them, whichever performs better in terms of accuracy or in terms of balanced accuracy or in terms of area under the ROC curve, it identifies them and that will give me the best possible model and then use that model to test it on your testing data. So that is how a typical support vector machines works, right? So probably I want you to practice it out. This will take a lot of time. Support vector machine, they'll take a good amount of time for execution, especially if it is not a linear kernel. If I go with a polynomial kernel, it will take a lot more time. That's the reason I have knocked out polynomial kernel. But if I'm going with an RBF or sigmoid, also it will take a significant amount of time. So probably depending on your system's performance capabilities, if you are working on your laptops and all, so you may want to enable some of them. But at least from support vector machine, grid search, if you want to execute grid search with too many hyperparameters, then it is always suggested to go with a high configuration or go with a GPU instead of a CPU. So those are some of the other things that you may have to take into consideration with respect to the hardware requirement, etc. Right? But yeah, you can very well uncomment these lines and you can very well try executing this. Right? Possibly, if possible, I'll also try executing it overnight to see what would be the kind of a result that I can get on this data. Are they going to really improvise over and above what is being provided by the logistic regression model? All right. So I'll stop this here for today. I hope you got, of course, there was some delay. We'll try to cover it in some other sessions. So in the next session tomorrow, I'm going to talk about the decision trees, as well as, if possible, we'll go into the random forest as well, because decision trees is not as complicated as it's a very simple algorithm again. So we will try to look at the decision trees and also get into the random forests as well in the tomorrow's session. All right. So if you have any questions, you can ask me, or if you want to practice and then you want to ask some questions, that should